This is Jack Jackson, and we're going to review the shortcut properties of derivatives that we have developed so far. For my survey of calculus classes or business calculus type classes which do not have a trigonometry prerequisite, this is going to be the entire list of properties. Okay, so in first, a word about the letters. If F, G, U, and V appear, they are functions of x. But when you see B, N, and C, B, C, and N, those will be constants. And I've been rewritten everything in terms of the chain rule, so I've written those out throughout this set. So we have two basic kinds of rules. The first kinds of rules don't actually find a derivative. What they do is rewrite one derivative problem as an expression that has one or more derivatives in it. So these rules here at the top are that kind. And then these others down here actually tell us how to actually find derivatives, but I've rewritten them in terms of the chain rule as well. So let's just review what we've learned so far. The sum rule says the derivative of sum is the sum of the derivatives. That's the derivative of f of x plus g of x is f prime of x plus g prime of x. The constant multiple rule says the derivative of a constant times a function is a constant times the derivative of that function. So the derivative of c times f of x is c times f prime of x. And then it gets a little more complicated, but not too bad, for the product rule. The derivative of a product of two functions, f and g, is the first times the derivative of the second plus the second times the derivative of the first. So the derivative of f of x times g of x is f of x times g prime of x plus g of x times f prime of x. And this can be generalized to more terms. Here it is for three terms. I've rewritten it in a slightly different order, but you have f, g, and h each time, but one of them has a prime each time. So it's f prime times g times h plus g prime times f times h plus h prime times f times g. So if you look at that in general, what do we have? We have the derivative of a product of a bunch of functions, function f1 up to fn. What do you get? Well, you get basically a sum. So we have three, notice up here we have three factors, we have three terms. Here we had two factors, here we had two terms. And each term has the same number of factors as the original one, but just one of them is a derivative. So what we're doing is, the outer thing is a sum from j equals 1 to n. We take the jth derivative, and all the other ones where k is not equal to j, we just multiply the original functions by that jth derivative, and then of course then we add all that up there. So that's a generalized product rule. The quotient rule says the derivative of the top over the bottom is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom square. I kind of write it this way so I can remember the bottom is all kind of this little V shape on the outside here. The bottom, what's in the denominator, stays in the denominator and is squared. And I start with the part that's no derivative, then I put the derivative second, just like I write the product rule of two functions. And then, of course, the subtraction will be going in the right way. A little fun little rule, if you want to remember this, is the derivative of high over ho is ho-de high minus high-de ho over ho-ho. The chain rule kind of permeates everything. It says if we're taking the derivative of a composition, f composed g of x, that is the derivative of f of g of x, that's f prime evaluated at g of x times g prime evaluated at x. Or the way I really think of that is in terms of doing a substitution, so I think of the chain rule as being the substitution rule, and you let u be some function of x where you substituted, then you get f as a function of u that looks more reasonable, and you take the derivative of that as a function of u, evaluated at u, and then you multiply by the derivative of the u with respect to x. The inverse function rule says if we have the derivative of f inverse of x, this is not an exponent, this is an inverse function, the derivative of f inverse of x is 1 over f prime evaluated at f inverse of x. So all of these rules rewrite a derivative in terms of one or more other derivatives. Then we have the things that we actually know how to take the derivative of, and there's actually a very short list here, really. Derivative of a constant, 0. The power function says that we have a variable base and a constant power, so use a variable n as a constant. We've done a substitution here perhaps to get it in that form. then what we get is n times u to the n minus 1, and then times the derivative of that variable base. An exponential down here, on the other hand, is, let's do this one down here, the derivative of b to the u, where b is a constant and u is a variable, is b to the u times the natural log of b, and then times the derivative of that u. Specifically, if the base is e, remember log of e is 1, so this reduces to the derivative of e to the u is e to the u times the derivative of the u. The derivative of the log of absolute value of u is 1 over u times the derivative of the u. If you didn't have the absolute value, that would be just 1 over u du as well, but we would have to make sure that u was a positive number. We'd have to put that restriction. And really combining many of these is the generalized power exponential rule, which says the derivative of u to the v, where these are both potentially variables, is n times, no, that's not, it's supposed to be an n. That's supposed to be the power here, which is v, to the power u, times u to the power of v minus 1 times the derivative of the u, plus the log of u times b to the v. See, that b should be a u. There we go. Times the derivative of v. Okay, that's right. So notice, in fact, really this, if you think of this generalized power exponential rule as including both versions of the exponential rule and the power rule, then we're really just down to 3 rules. We've got the general power exponential rule, the logarithm rule, and the derivative of a constant is 0. So really just basically 3 rules there will take care of everything for things that you can actually do. So basically you have to get it to where it looks like a base to a power, one of them variable, both of them variable, whatever, or a derivative of a constant, or derivative of a log before you can do it. And then if you rewrite through a series of substitutions or a series of these rules up here, then you basically get it down to one of those things that we know how to do. So those are the basic rules, and we can do lots and lots of problems with these rules. And in the next video, I'm going to do a whole bunch of examples using these rules. Now, if you're in Calculus 1, say my Calculus 1 class, we'll go on in subsequent videos to learn how to find some derivatives of some other things like trig functions, inverse trig functions, and hyperbolic functions. And so that'll require a little bit more derivation and a little bit more further examples. But I'm going to stop here for the survey of calculus class, and for both classes we'll see a bunch of these rules applied in the next video.